Okay, so we can say a little bit about how the lecture format should work here. So I take a look at the survey of the Hug School. So I see that our group is very diverse. There are theorists, people doing experimental, and your experience in the school with nuclear physics is very diverse. So that's why in this lecture as experimentalist, I will just cover a very basic level for PhD student. So with that idea, so I will try to use very little formalism and introduce more concept, like conception and including the experimental information. And I want to present the experimental result, also explain their interpretation. So for style of the lecture, it will be informal, like I encourage you guys for the interaction, and you can interrupt anytime if you have question, or just unmute and just ask it during the lecture. Don't need to wait until the end. So I think that listen for the 1 hour is kind of long. So I will give the talk maybe around the 45 to the 50 minutes, and then we can have some question as well. And in this lecture, I put a note here that because many slides I adapted from my different collaborator, and I would like to say thank you to them for their support as well. So in case you can go around and see the slide somewhere, you know where it's come from. Okay, so we will have a 5 lecture. I will give the 5 lecture. So this lecture, it will focus on nuclear structure and specifically in the short-range correlation. So in the lecture 1 we have today, we will have an overview of the electron scattering probe. So that's the only probe we are using and discussing in this lecture. And for the lecture 1, we will have an overview of some of the physics channel like elastic scattering. And I will give us some example about what we can do with elastic scattering. And we will have an overview of what's the elastic scattering, as well as some example corresponding with that channel. So that is for today, and tomorrow we will jump into the core of the lecture 1 is about short-range correlation. So for that one, I can have an introduction about short-range correlation and what have been studied, what we know about short-range correlation through the different channel, different type of measurement, and then we will go into something called the nucleon interaction in nuclei, what we can use to study short-range correlation. And for the next day, the lecture 4 and 5, we will study some application of or connection between short-range correlation to some other effect like EMC effect. And we will discuss a little bit more about next generation of the short-range correlation experiment. And in the end of lecture, I may take like 20 to 50 minutes, we all can watch a movie together. I call it movie, but technically it is the proton movie. So this is some the project combination between scientist and the filmmaker to introduce about like how to help you to visualize how the proton look like. And I think it's very interesting. So I would like to advertise that video with you as well. So now let's start with our lecture 1 for today. So in this lecture, we would like to use the electron scattering as a microscope in order to study internal structure of nuclei. So the goals of this study is that the electron scattering can be used to study internal structure as a dynamic. Dynamic here means that how they interact together inside nuclei of a complex object. So object we are talking here is a nuclei. So what does that mean? So it means that we will use the high energy scattering electron. So you can see it here, like high energy electron with the four momentum vector here. It come in and scattering off from different nuclear target. It can be any different type target to the exchange of virtual photon with the four vector we call Q here, and scattering off with outgoing particle here. So in this collision between the electron and the nuclear target, it can break the nuclear target to different type of particle. So all particles after collision, including the scattering electron, we call it the final state particle. So what we are doing in experimental is that we will detect all of the final state particle. We can detect different information. The mainly will be the momentum, angle of the final state particle. And from the detected information, we will able to reconstruct it. Reconstructed here means that using the detected information in order to calculate other like physics variable. So using those physics variable, we were able to infer what is going on inside the nucleus and learning about its structure. So that is the general picture, the general idea about how we are going to use electron scattering air abroad to study nuclear structure. Okay, why not go to the next slide? Yeah, so in order to help you to have a more like a logical picture about how we going to do this study. So theory and experimental all the way working together, and I call it very much like flowchart of the scientific method. So in terms of the theory, they will have a different hypothesis. So with each of the hypotheses, they can have an expectation for different behavior of nuclear structure. So that is from theory side. And then from the experimental side, what we will do is that we will collect the data in order to test the theory, testing different hypothesis theory here about nuclear structure. So in order to collect the data, we need to have experimental tool. So here is one of them we are using in this lecture, is electron scattering. So how does the flow work? It's like as you can see this, we will have a different hypothesis from the theory side. For each of hypothesis about what is the internal structure, we will able to predict some of the observable, how it should look like in the experimental side. So from experimental side, we don't know what exactly inside there. What is the real one? What is the true hypothesis? So we only do the measurement. So from the what we measure, what we will do is that we will compare with the prediction from the different hypotheses. Then what we will do is that we will do the comparison, follow the scientific method is it. So we collect data, we will compare what we measure with what is predicted based on different hypotheses from theory side. If it disagree with each other, we reject that hypothesis. And if it agrees with each other, we will accept that hypothesis. So it's very much like a puzzle game here. So by assuming and keep doing this feedback loop, we will able to understand different perspectives of the nuclear structure one by one. Then when we agree with one hypothesis, we know that we understand one aspect of nuclear structure. And then we continue adding in another hypothesis. And then we will able to complete the picture about how the nuclear structure look like. So that is scientific method about how we do experimental compared to theory in order to understand the nuclear structure. So now we talk a little bit more about the electron scattering at the microscope measurement. So when you have an object, you have a microscope, zoom it in order to see structure inside there, right? So you will have something very much like a controlling system. You will have a different knob in order to control so that you will able to control what you are seeing inside that object you want to study. So it's similar here like that. Electron scattering, it also have its own the controlling system. That one is determined by different kinetic variable. I listed 3 of them here. So the first one, it is the Q square. So this Q square is the minus of the square of the 4 transfer vector Q I introduced earlier. So this is playing the role at interaction scale, very much like resolution. and we will go into it more later. And another variable is XB. So it can be calculated as Q squared divided by 2 MP nu. So I have an inconsistent in my notation here. So the nu here, it is the energy transfer. Nu is similar, like the same as the W here, the omega here. They are energy transfer. So this energy transfer is the difference between the incoming electron energy and outgoing electron energy. So that is omega or nu here, is energy transfer. So how should we visualize, how should we understand this variable in terms of daily language? So I mentioned with you that Q square, it plays the role very much like resolution. Right? So when we think about resolution of microscope, it means that better resolution, you will be able to see smaller objects. So it very much like here is some of the object like materials, the structure. This it will be the resolution of it like around 100 eV to 100 keV. But now with the nuclear, it's much smaller structure, then we need a finer the resolution scale. It presented by the Q square here. So for example, at one the level of the Q square, you will able to see the nuclear as the whole object itself, let's say. But now if you tuning this knob and increasing the value of Q square, means that you have a more powerful resolution, then you will able to see smaller object inside the nuclei. So at this level, you will able to see the nucleon inside the nucleus. And then if you continue increasing the Q square, you will able to see even finer structure of the nucleon. It's like quark, gluon, and other stuff. So the Q square, it plays like role and resolution, and you can understand that, oh, higher energy, higher Q square, you can have a better resolution. And it depends on what is the value of Q square you can control in the experimental. You will able to see different aspects of the object you want to study. So we able to select the spatial resolution and excitation energy independently. So I mentioned that this electron scattering like interact with nuclear target to the exchange the virtual photon, right? So that virtual photon presented by that transfer for vector, it have an energy component nu to omega, and it also have a 3 component, the momentum Q vector there. So you can think about it like in terms of virtual photon, it also you can calculate the weight blend of that virtual photon to this equation. And it depends on the wavelength and or value of the Q, you will able to access to different the resolution scale as I explained in the previous slide. So we can divide it by 3 the region. So if we have a low Q value, so it means that that photon wavelength is larger than nucleon size. In this case, we only have a resolution to study the nuclear as a host object. So now in the medium value of Q, around from 0.2 to 1 GeV. So now see the wavelength of the virtual photon, it will be almost the same size as the nucleon, the radius of nucleon. So then we will have a nucleon resolvable like resolution. And now if we increasing the Q to the high value, like larger than 1, then the wavelength of the virtual photon is smaller than the radius of nuclear size. So then you will able to study substructure of nucleon. So it from the general concept to very quantitative value about the Q value you can use to control your resolution in the experimental. Yeah.
Dien, can I ask a question?
Yeah,
so
sure.
for photons, E equals P, so I would think can you really select them independently, or is this like a different way of looking at is the spatial resolution just a different way of looking at the energy resolution?
So this one, in terms of spatial resolution, it mainly depends on the Q only. But like you see that this is the 4 vector, right? So energy term, it will depend on energy of coming in and outgoing. And the momentum, it also it separately depend on the momentum term of that 4 incoming and outgoing vector. So we can independently just select the omega value and the Q value. Yeah.
But you can't increase one without increasing the other, right?
For the virtual photon? For the virtual photon.
Oh, okay.
Yeah,
Because
for
E
the
is not
virtual photon we can.
Okay.
Yeah.
Okay,
Okay.
thanks.
Yeah. Okay. So now
Yeah.
the question.
Hello. I have a
Yes, do you have a
question.
question? Yes.
Yeah, about the low Q, what are study in this case, in the case of the low Q?
Can you say it again? I didn't hear you yet.
Okay. Can you explain what are study in case of the low Q? I mean, if the wavelength is not small enough, then we cannot probe the nucleon. So I'm not sure to
It
understand.
like this, huh? It like this. So the wavelength, right? So now, for example, this one you have radius of the nucleon. It is like this, the RP in this slide, right? The RP here. So you will have a radius of this one. So it really depends on the wavelength of the virtual photon. So now the virtual photon with the wavelength is larger than this, the nucleon, the radius one. So actually we're not able to see the structure of this one. So only the structure we will see as the nuclear, as the whole structure like this. Does that make sense?
Yeah.
Like, yeah. So it needs to be like smaller than the size of object in order to look inside that. So that is the kind of like simple way to understand it. Okay. For example, if you want to study the nucleon, so it has the size, right? So then the wavelength of this one, it needs to be at least smaller than or equal to the size of this one. So you can see the inside of this object. But if it's larger than that, you will not able to see this phi structure. Okay. Did I clear your question, Matthew?
Yeah.
Okay, so we continue. All right. Okay, so we explained about we want to use electron scattering as the microscope to study internal structure of nuclei, and then how we control it using the spatial resolution and stuff, right? Then now the question is that why we use electron? So what's the advantage of that? And the answer for this question is that electron is the point particle. So it is elementary particle. It doesn't have an internal structure, right? So using that as the broth, we know the broth structure already. We understand it. You can think about that. You use A to study B. And if you don't know both A and B, then it will be much more complicated picture, right? But if you use A to study B, at least you know A already. So only object you want to study is B. So you only have a half understood already. So that is a simple way to understand that. Another thing is that we know that the interaction of electron to the nucleus there, it is to the virtual photon exchange. It is the electron magnetic interaction, so QED. So it's well understood, right? So you can go from the elementary particle like this one, they explain about QED, and this one is the most understood so far, the interaction. But that is the good thing about using electron, and this interaction is so weak, right? So it means that electron will not interfere with the structure of the nucleon. So we can use electron to study the structure of nucleon. And the theory also work too. The theory here, I mean like one photon exchange. Like what we have been talking about, we assume that electron interact with nuclear target through the one photon exchange here. And because of all this one, the electron is a great choice in order to study the nuclear structure. But of course, it also has some disadvantage, like a cross-section are small and electrons radiate. So that is some type of correction we need to take into the account if we want to understand nuclear structure. And I will come back with issue about the cross-section are small here and how we're going to handle that. So that a little bit more about the photon. So I mentioned earlier that the incident, like incoming electron, like interact with nuclear by the virtual photon. So what exactly the virtual photon mean? So when you're talking about the photon, you think about it like zero mass, right? But now the virtual photon is slightly different. Yep. Someone have a question? Okay, so the virtual photon here, so it means that the momentum of that photon is larger than energy. So then when we calculate this Q square equal to square of this 4 transfer vector, the value of it is larger than 0. So it very much like we have a virtual photon, it has mass. So that is different compared with the real photon, because when you talk about the real photon, it has a 0 mass. So that is something you pay attention when you hear about the virtual photon. They have a different compared to the real one. Okay. So now with electron, using electron at the microscope.
I have a question.
Oh yes. Yeah.
Yeah. Okay. The electron can also interact by weak interaction.
Yes.
Actually, yeah. By the exchange of Z boson. Did you know the, let's say, contamination rate in how often it occurs, this type of interaction?
Okay, so we have a both like the weak interaction by exchange the boson, right? And so the for photon too, right? But here we only thing we consider in this one is the virtual exchange, the virtual photon. With the exchange the W boson or Z boson, that one it will go to the weak interaction. So that one is something we not consider in this lecture. Okay.
Okay.
Yeah. Okay, so in order to use it electron to study internal structure, we need to have some requirement on the electron beam. So the first thing they need to have a high energy. So I mentioned with you before that when using this Q, it can calculate to the approximately equal to the equation. And then we would like to have the Q squared bigger than 1 GeV so that we have enough resolution in order to study nucleon structure or like substructure of nucleon, right? So that's why with the required electron beam have a high energy here. And then in terms of accelerator side, what they call is that the high duty circle here. So in no large beam current variation. Then by doing that, they can have a reduced accidental coincidence for multi-particle detection and reduce the detector rate and multiple hit. So this one is the requirement for the kind of accelerator and also detector side. And they also need to have a high intensity because of we have a very small cross section. So I will come back to this high intensity later. And they also require to have a high resolution so that we can separate the different nuclear level. And they also good to have a polarization. So for polarization here, it will relate it to the spin asymmetry measurement and understand the spin, the structure of nucleon. So that is something we not discussed in this session as well. But if you are interested in the spin study structure, it is very interesting as well. We can talk offline about that, but I will not have enough time to cover everything in this lecture series. Okay, so now there's one concept. Everyone assumes that it is trivial and clear to students. But beyond my experience, actually, this is a more confusing concept for a student. And I think it's good to understand it from very beginning. So for the student, it's good in both for theory and experimental as well, because it determines a lot of important thing about how you design your experiment. So let me make it clear. When I talk about luminosity, I will break it to the different portion. So the first one, we will have electron beam coming in to interact with the target, right? So the first thing we will have we call the electron beam luminosity. So we will when we send electron beam to interact with the target, we will have an electron beam current. So when you have the current there, for example, 2 like microamp, 10 microamp, something coming hit to target. So from the current of the beam, you can convert it to the number of electron per unit of time. So what I call here as the luminosity of the beam, it should have unit of invert of the second, right? So in order to calculate that, you will have a current of the beam there. Then you will divide by the value of the electron charge. Then you will be able to convert it to the number of electrons per unit of time. So that is what you call the electron beam luminosity, number of electrons per unit of time. So you can take that as the LB. Second one, now that beam come to interact with the target. So the target here, it will have a different shape, right? And it have a density. So when we talk about density, it is like volume density, like gram per cubic centimeter or something. But what here we will call it thickness. So thickness of the target is the areal density. So it is, for example, like you need to multiple of the volume density in the gram per like here. I have a typo here, sorry. It shouldn't be the minor here, yeah. So then you will multiple with the length of the target, and then you will divide it by the atomic mass. And then you multiple with Avogadro number. Then you will able to convert the thickness or areal density in terms of number of particle in unit of area. So here, there are something it can confuse you is that the number of particles, you can either calculate it in terms of number of nucleon or nuclear. So now, what is every facility? They will tell you that, oh, we have a great luminosity. That is the total luminosity. So it is the number of the electron and the particle interaction per unit of time, per unit of area. And you can calculate the total luminosity at the beam luminosity multiple to target like luminosity. Is that clear so far?
Can I ask a question?
Yep.
Okay, so in the first bullet you have electron beam luminosity. And if I concern about the beam current, like if I say 65 microamp, why do I care about electron beam luminosity? Because they're eventually the same thing. So why do I care about electron beam luminosity?
So I just tried what we care. Indeed, it's only the total luminosity. But because of the total luminosity, it depends on how high the beam current you go and how thick you can provide the target and how much the beam current the target can handle in different facility. So that's why I try to break the total luminosity in the different parts to help you to understand what go into the total luminosity better.
But still, a beam current will have the same information as the electron beam luminosity. Is that right?
Yep.
Okay.
Correct.
Okay.
Yeah, it is like in terms of different unit and how you determine the luminosity. Okay, in terms of conception. Okay.
Makes sense. Thank you.
Yeah. And this total luminosity is, in my point of view, it is a key quality in order to design the experiment. Because of why? Because the total luminosity multiple with the cross section will give you what we call event rate. So now, for example, if your advisor send you to some facility, they know the luminosity of facility. And then now he can tell you what is the physics process you want to measure. So for each physics process, you will be able to calculate the cross section from that process. Then you will be able to calculate the event rate. So this is how people estimate the time, make the run plan for experiment. All the thing, it depends on how this event rate look like, right? So for example, if you have an event rate, it's a 10 event per second. So then if you want to have 1,000 events, you know how much time do you need. And this one will determine like, what based on the statistic, it means that how many number of events you want to have for each of the measurement, then you will have a small enough the statistic uncertainty. So this is where statistic uncertainty comes from. It depends on number of the event you collect from the experiment. So up to this point, I think that you will have a confidence to design or calculate the runtime for the experiment if your advisor sending you to the different to design some experiment. So we know about the luminosity, and we will spend much more time to understand about the other term is the cross section that really carries the physics. Okay. So we have all over the world, we have many different electrons accelerator. So we have the MUMMI in Germany. I never been there, even though I want to go there someday. We have a Jefferson Lab at where you are now, and the many other past and the current one. And we are going to build a new one is EIC. I think that you have heard about it EIC a lot during the school, and I will come back to talk with you more about EIC in the end as well. Yeah. So because you are here at Jefferson Lab, so I give it a little bit more favor by giving it a little bit more introduction. So you know that it's located in Virginia, where we are here now, right? So this electron facility can provide the beam from like 1 to 10 GeV electron beam. And then the special thing is that we can provide both provide the beam and the target. Like this one is very important for spin study again, but it will not be covered in this lecture. And we have 4 different experimental hall. So beam is I don't know if you took the tour during the J lab yet, but here is where the electron beam is ejected, and then we will go to the accelerator side until it gets the required beam energy, and then it will get sent to the different experimental hall A, B, C. I think I'm not sure if you already go to see the different experimental hall yet, and we also have a new hall is the hall D here. So each of these experimental hall, they have a very like comprehensive the physics program to study different aspects of nuclear physics. Yeah. So now is we have a electron at the tool. We have a accelerator side. So now we do the measurement. So when you hear the people say that, oh, I doing the EE bright, I doing inclusive measurement, I doing the knockout measurement. So what is that? What does all that mean? So I think it's good to know how they define the name for different measurement. So it really depends on what you detect for the final state particle to determine the name of the channel you measure. So the first one, so simplest one is that you only detected the outgoing particle. So that one, we will call it EE bright. So you see that this one will lit it, the final state particle you detected. And for this simple channel, we call it inclusive scattering. So you may hear it many times, but that is what is E. So we also can detect the leading proton. So what that mean? So we will knock out in this proton inside nucleus and it coming out, and we will detect both of the outgoing particle and the knockout proton. Then that channel will be E prime P measurement. Or if we detect more particle in the final state, it can be E prime and N. So N here it can be proton, neutron, and other. So this is how we call or we define the name for different type of measurement. So this is in terms of what you detect in the final state particle. So when you see, say, oh, I'm doing this measurement, that measurement, you know, oh, that is what you detect in the final state. So when I join the field, people keep saying, oh, we are doing the inclusive, we're doing exclusive. And I had no idea, well, what did you mean by that? So I think like, oh, it's something, it looks kind of like trivial to some expert, but for it, I think it's better to clear it from beginning, because we will use this concept a lot along the talk. So you know exactly what we are measuring. Yeah. So now is that in terms of measurement in the final state particle, and now how about in terms of physics? So now what I'm showing you here is E prime, the inclusive cross section as a function of the omega transfer energy at the fixed momentum transfer. So this is the toy model. So when we call this cross section very much like physics response function, right? So it means that it depends on the different type of the reaction that electron interact with nuclei, and it will depend on the omega variable here. So with the different omega, you will see the different type of physics. So for example, if the omega here is equal to Q squared over the 2m, so that one it will be elastic. And then if it's increasing, it has some resonance, another resonance, and it will be washed out by something we call deep inelastic. So this is very much like toy model for the interaction of E prime as a function of omega on the proton. So it will slightly change when you go to the interaction of the nucleus. So the nucleus here is a combination of the proton neutron, and it is a binding energy, right? So that is making it a little bit different. So the cross section here, the response function here, it will slightly change. So it will have elastic here, it will corresponding with the Q squared divided by 2 times of the mass of that nucleus. And then we will have this giant resonant one, and then we will enter another physics area, it was elastic, and they have a kind of broadened peak here. We will talk a lot about this one later. Then we will have a different resonance here, and it also was out by the DIS reaction here. So it have a two-thing combination here. You shouldn't mess it up. The first, what type of channel, what type of measurement we are measuring. So that is the depend on the what the final particle you detect, like E prime here. But for a given the measurement, it will depend on the different physics. Even in the E prime P, when you're changing the omega, you will improve different type of physics. And it depends on the what type of physics region you are like measure, you will study different aspects of nuclear structure. All of them, all these physics regions are important, and it can help us to understand different aspects of nuclear structure. Everything is interesting, but in the hour lecture, I saw what I'm doing research. I will always focus on these three regions: the elastic, quasi-elastic, and the deep inelastic region. We will not talk about other regions at all. And I is not an expert for the other region. Yeah. So now try to yes.
Yes, sorry, thank you.
Yeah, sure.
Can you say which nuclei are we considering here? Are these deuterium or heavier nuclei?
We will study all of them. Yeah.
Okay, thank you. But
yeah.
in that case, wouldn't the resonances at the lower energies be different for each nucleus?
So for resonance, this one resonance, which one you're asking?
I guess I'm thinking of, I would think that all of the structure below the nucleus region would be different for depending on which nuclei you have.
Yes, it will have a different property. Yeah.
And then which graph are we seeing here?
So this graph is that you can think about it's just like toy model. It's kind of genetic. So you can see that, oh, okay. So for Z kind of energy at the fixed momentum, you expected to see elastic. And around here, if the energy lies at this level, you will see the quasi-elastic. So it kind of like for the different the Q value, so this one it will shift to different location. I will come back to it when we study different nuclei. So for example, you will see exactly where the location of the quasi-elastic peak for different nuclei or something like that. When
Thank you.
Yes. Any other question?
I do.
Yeah,
so
sure,
what?
Erin. Yeah.
What's the giant resonance, and why are there smaller peaks near the elastic peak?
Oh, so this giant resonance here, it more like different distinct the excitation of the nuclear state. Like when you put it to give it more energy, it kind of excites something. So it has this type of giant resonance up there. Okay. Yep. And now we talk about all this a little bit more because of the name may confuse you. You may want to understand what exactly elastic mean, what a quasi-elastic mean, and what the deep inelastic mean in the daily language. Okay, did I answer your question, Erin, or you still confused?
Yes, thanks.
Okay, yeah. So so we will focus on these three regions. So what are they? So when also, I don't know in your opinion, but in my opinion, whenever I study some physics concept, I would like to think about it in kind of daily language a little bit. So it helps to have an easier visualize picture in our head of what exactly is going on. So I will try to make it like a simple picture, like to help you to visualize it in your head a little bit about this physics. I'm not guarantee I can do it, but I'll try. So I think we already talked about that a little bit before. So the elastic here, what does that mean? So elastic here means that electron coming in interact with nuclear, but it only provides enough the energy to make the nuclear recoil. So for example, electron plus with proton, then in the final state, you will have outgoing electron and still proton. So it means that it only have enough energy to kick that nucleon and make it recoil out. So that is how it looks like the elastic, the scattering to you. So for elastic scattering, we can use it to study the structure of the nucleon or nuclei. So nuclear, you think about hydrogen, right? So hydrogen, it's not a proton. So we call it the nuclei, but actually like it is a single proton. So we can use the hydrogen to study nucleon, like proton structure. And then we can have a nuclear of the neutron or heavier nuclei. Then this elastic, we take that nuclear as the whole picture, knock it out and it recoil. So that is how we can use it elastic to study the something we call form factor, charge distribution, and we can come back to that later. So that is the first channel. So now what is different in the quasi-elastic? What exactly does that mean? In a simple way, you can think about quasi-elastic scattering is the electron coming in and elastically interact with a single nucleon inside nuclei. So then it interact with a single nucleon inside nuclei, and there one thing is different, is that this nucleon is moving inside nuclei. Because this nucleon is moving inside nuclei, then it has information of the energy and the momentum. Then this quasi-elastic scattering is a channel we can use to study how the nucleon moving inside a nuclei. So that one is related to something we call cell structure and momentum distribution of nucleon, and it will be used to study short-range correlation, the main topic of our lecture too. And then now we go to deep inelastic scattering. So deep inelastic scattering, it means that we have resolution enough to go inside this nucleon already. So now it kind of like electron, now it interact with the quark inside of this nucleon and knock it out, right? So that is how we have a deep inelastic scattering. So with the deep inelastic scattering, we were able to study the substructure of nucleon. And then we will see, oh, how the quark and gluon interact inside this nucleon to form a nucleon and its characteristic. And then how that one will form together to make nuclei. So they at the different 3 levels, but they kind of combine together to make a big picture. Okay, is that clear to you about what is elastic, what's the elastic and deep elastic? If it's not clear, at least I hope you get some idea about what exactly is going on. I need some feedback. Is that somewhat clear to you? Okay, good.
It's clear, but what EMC stands for?
EMC. Oh my God! Now you need to. I need to try back. It's some Europe. Oh my God! Let me get back to you later.
The European muon.
That's fine.
I call it
Yeah.
EMC all the time, and I forgot what it's short for. Okay.
Or European muon
European muon collaboration or
I see.
something like that.
Thank you.
Yeah. Okay. Yeah. We will have a lot of time on that. All right. Are you guys tired? Do you guys need a break or can continue?
Yeah, please continue.
Okay. So I hope I don't let anyone fall to sleep yet. I hope not. Okay. So this is
I have a question. So,
yes. How you? Yeah.
then what is nuclear modification?
Nuclear modification. Okay, we talk about it a lot later, but I can give you some information.
Mhm.
So when nucleon stay alone, we call it a free nucleon. Like it has no interaction with anything, right? And we bring that nucleon combine together to make nuclear. And the behavior of this nucleon change based on the what nucleate inside, and that is called nucleon modification. It does mean that nucleon behavior different when it bound together to make nuclear compared to when it stay alone. So that is the daily language explanation for nucleon modification. And it's very interesting topic too. We will go to talk about it in the lecture 4, okay? Okay, so now we continue. So now we said that we're interested in the 3 regions. So let's jump in one of them. The first one, elastic. I hope that the picture still stay with you, like you get some idea about what elastic mean. It coming in and it see the whole thing as a picture, like whole thing. So what we want to study with it elastic scattering is what we call charge distribution. And second thing is the form factor. When you hear about distribution, it means that you say, oh, the charge distribution, the momentum distribution, what are they? So when we talk about charge distribution, you can think about it in terms of probability of finding that value of charge with that, like probability of finding the charge with some value. So that is a simple way to think about it. Or even momentum distribution, it is a probability to finding that given value of momentum inside nucleon or inside nuclei. So that is you have an initial idea what is this distribution mean. Okay. So this is like very high moment, high energy electron, it's very high relativity. So, but it has some connection to classical picture. And I think when you talk about classical picture, you You have learned a lot in undergrad as well. So we think about electron, it's not just a particle, it also a wave, right? So it's very similar like a picture. So now when we talk about wave, we will have a wavelength. So now we have electron energy like EE. So then you can calculate the wavelength. We mentioned about it very early in the lecture too. So we can calculate the wavelength of this electron. So you can think about it in both particle, electron, and the wavelength of that electron. And then in order, with the high momentum unit, we're using the different type of unit, the natural unit there. So then from the energy of electron, we convert in this unit, you will able to calculate the wavelength of the electron. So this wavelength is a resolving scale. So now in the, how we connect it to classical picture. So you can think about electron beam is very much like the light. So when you shine the light on the disk here with the side of the 2A, and then you will put the screen behind it, and then you will observe the diffraction pattern in the screen. This one is familiar to you, right? So I think that you take this one in undergrad class. So when you're observing the pattern in this screen, you will be able to find the amplitude of the wave on the screen. And it will look something, we have the pattern, it look like this. So what you calculate is intensity, it is square of that amplitude, right? And then you will be able to determine the first zero, like the first minimum in the pattern there. You determine the distance to the central there. And with some of the math, you will be able to connect between the side of the disk, the wavelength of incident light, and this one is the angle corresponding with the first zero, the first minimum. So that is what you do in classical picture. You know wavelength, you know the first zero, you know the angle corresponding to that first zero, you will be able to determine the size of the object. So that is the classical picture. Very much similar to electron here. Similar, but not the same, right? So now you also have a incoming electron with the energy. You're able to convert it to the wavelength, like I just mentioned, right? So this wavelength electron coming here, it will interact with this nuclei. It has the size of nuclei. Then we detect it like scattering out. So you can think about it like the screen here. And then you can find the minimum too. So this is the distribution we see from the electron scattering measurement. So it's the response function to the cross section. You can think about that like intensity in the classical picture. And then you will have the value of the Q here. And then you see, oh, you also see the pattern of it, like you have a first minimum. So you determine the first minimum is corresponding to the what value of the Q. And what is the angle it corresponding to? So you will have a z at the theta mean, right? And then you have electron energy. You convert it to the wavelength. So then it's just a simple picture like you see in classical. You can put it in formula and can calculate the size of this object. So the elastic scattering, it can help you to determine the radius of the object here. And with it very simple calculation, like in the classical picture, you get this one, like I forgot, it is the radius of the of what nuclei. But then you will compare with the real measurement, they very close to each other. So this elastic is a very good tool in order to determine the size of the nuclear object you want to study here. So that is one example about how we use elastic scattering in the study the nucleon structure. So now I'm talking on. Oh yeah, sure.
Hi. So this doesn't give you, elastic scattering can't really give you information about how charge is distributed within the nucleus, right? Just a radius.
That is the first thing is the radius. Now we go to the form factor, charge form factor. Okay, in the next step. Yeah.
Excuse me.
Yes.
Yeah. So I wanted to know, how did you calculate the y-axis, like this sigma over sigma mod?
So this is the cross section, right? So this is cross section is what is you mean the mod here?
Yeah.
So the mod cross section, I come to it very soon. Okay, so give me 1 more minute. I introduce the mod cross section soon. All right. So this is the general picture first. It's coming soon. All right, in the more detail. 5 minutes.
Yeah, because it's already 1 hour.
Oh, really? Oh, I talk too much. Sorry. Yeah.
You can go ahead for a while. I mean, it started a little bit later.
We have another thing on the schedule.
No, not really. That's why I told you can go ahead for a while, but would not keep them forever.
Okay, I see. Do I want to continue or want to take break and continue tomorrow? Are you tired? Continue. Okay. So let's continue for maybe 5 more minutes and then we can start over tomorrow. Okay. Okay. So now we think about this picture. Like Erin just bring up, like what is the charge form factor? So let's do the elastic scattering in a more formalism and more kind of like formal way. So what do we call it? The Fermi golden rule, right? So we can calculate the cross section, but now what we assume is that the nuclear is the nuclear or nucleon is just a point-like object with infinite mass. It means that it will not move. The electrons will come and interact with this object. And this object, it will have a charge distribution we call rho x here. So the x here is like depend on the location of it. So now what we want to do is that, or we want to do is it elastic in order to see how the charge distribute inside this object, assuming this is the nuclear you are scattering up. But remember in the mind, we take it like point-like we take it like infinite mass, even though it is not true, but compared to electron mass, this one is way heavier. So it is reasonable approximation. So the cross section, based on this rule, it will calculated by square of the scattering amplitude. We don't need to know detail. That you can check out later. The talk about conception here. The scattering amplitude square and density of the final state, what we call the phase factor. And then you will able to calculate the z amplitude depend on the wave function of the final particle and the initial particle. I will not go into the math here. So this calculation, the value of this one, it depends on the potential, the Vx we can assume the different Vx for this distribution. So now with this one, if we think about it like this object have a charge distribution is the rho x, then the Vx, the potential, it could be the Coulomb potential. Then you, from that assumption, you can assume the Vx equal to this distribution, it is equation here. Then you plug it into the amplitude. Then you will able to calculate like this. So what we call FQ equal to this part only. The part, it depends on the charge distribution, is FQ. So this FQ here is the form factor, like charge form factor. And this, based on this equation, we can see that the charge form factor is the Fourier transformation of the charge distribution. So technically, if you can measure, if you have a FQ, you will be able to extract to the charge distribution here. Or if you have charge distribution, you will be able to calculate the FQ here. So they calculate in both ways, right? So the thing is that now we will have the mode cross section. The mode cross section here it is a cross-section of electron scattering on the point-like infinite mass nuclear assumption. It means that this one, it didn't take into account of any the charge distribution or anything. The charge distribution is carried by this form factor, or in other way, the charge form factor presenting how the charge distribute in the object. So in experiment, we will measure this cross-section, and based on the assumption we have, we will able to calculate the Z mod cross-section. I will have a formula for Z mod cross-section later. And then we divide it one to measure to what we can calculate the mod cross-section. Then we will able to extract it, the charge form factor of that object. And that the charge form factor, from charge form factor, we will able to use the Fourier transformation in order to calculate charge distribution of the object. So charge distribution showing in this one, the solid curve is the calculation based on some assumption and the experimentally for different nuclei. So you can think about charge distribution. The charge distribution here is probability to find charge the corresponding with this R, the radius of the object, right, of the nucleus. So you can see that the experimental and the theory calculation agree with each other very well. So the elastic scattering really help us to measure cross-section, what will help us to extract the charge distribution, and based on assumption and theory calculation and experimental, we understand the charge distribution inside nuclei pretty well. So that is what we can do with the elastic scattering. And just to notice that in order to build it incoming electron or this spectator electron detection, all this one is a $10 to $1 million machine. So it's really expensive in terms of experimental as well. But as you can see, we know about charge distribution very well, and we are using elastic scattering for this type understanding. So I think I over time now, so we can stop here for today, and then we can continue it for tomorrow.
I think we can open for questions.
Yeah. Yeah, okay, so now I can open for 10 more minutes for the question. If you have any question, just unmute and ask me, okay? Yeah. Okay, let me see. Yes.
Who is Derek? Please go ahead.
Yeah, go ahead.
So thank you for the talk.
Sure.
I just had a question kind of going back to more of the kinematic variables. One other kinematic variable I've seen in these things is something called the like the virtual photon polarization called epsilon. And I know that's like a function of like the forward momentum transfer and the energy transfer. And I've always kind of wondered like what, like if that had any sort of like what the physical significance of that is.
Which epsilon variable you see in what in what slide? Can you point me to so I know?
Oh, it wasn't in this slide. I just wanted to like if you've heard of that before.
Yeah, so we have many different epsilon, and I will going to talk about one of that epsilon in tomorrow lecture. Actually, it's supposed to be one of the lecture too, but I kind of here, let me see if I have that epsilon here. Is it epsilon you're talking about? Yeah.
Yeah.
Okay, so can we wait for this one for tomorrow lecture, because I will going to talk about that as well. Is that okay for you?
Yeah, for sure. Thank
okay,
you.
sure. Yep. So Melanie, yeah, you have more question?
Yes.
Yes.
Okay. Thank you for the presentation too.
Sure. Yeah.
You say why you use electron for this scattering process, but why don't use, for example, muons if they have very similar properties to the electrons for study, for example, the form factors of the pion or the chi or the proton?
Oh, we do have that as well. We just don't do it at JLab, and I just don't do it in my research. So yes, you are right. We can use that as well. And all of that, both they have a different advantage and disadvantage too. But like it can be used, that's for sure. But like is that not what we are using here? That it is answer your question. Yeah. We have many different choice. It really depends on the what you want to study. And like, for example, like electron, it can be good for this aspect, or the muon, it can be good for another one. So I'm not the expert in terms of the muons both. So I shouldn't say too much about that, but I believe that we are using the muon for other type study as well. And it have its own advantage. Yep.
Okay. Thank you.
Mm-hmm. Yeah. Other question? Alex? Yes. Yeah.
Yes. Thank you for speaking. On this slide, are there any ideas as to the leading causes of the discrepancy between the experimental results and the mean field theory, or the leading order corrections to that?
So you mean the difference in the distance here? The
Yes,
short
correct.
one? Yeah. So actually the mean field, it have its own approximation, and we will discuss about this mean field later. And all the difference here, it calculates the short distance. And I think in the short distance, the mean field, it couldn't describe some of the property of the nuclei. So maybe that one of the sorts, it can create the difference here. But like exactly what caused the difference, I don't have answer for that. Yeah. So for each of the approximation, the answer, so the more like the answer is that for each of approximation, it can only work well in a certain region, but it cannot work well everywhere. Yeah.
Okay, I don't see any other question so far.
I still have one question for all students. Do you think that the material is too simple for you? Do you want, because I give a try to give a conception for you to understand what we are doing. So I just concerned that you know better than me after you listen to the talk. If you think that, oh, the material is too simple, I would like to adjust the level of complex up tomorrow. So it let me know your feedback on the, for example, now, if you think it's too simple, just raise your hand. So I know that how many people think it's too simple. So then I can adjust the lecture for tomorrow. Yeah. Okay, one thing is very simple. Two. Great. So how many raise the hand? Can you see every student? I don't know. Mm-hmm. Okay, yeah. So actually, it's just the warm up, and I think I go too slow compared to what I want, because from the next slide, I think it will be much more complicated. So from the tomorrow, it will be more like formalism, and then I think it will be more complicated. So today is the warm up for you. Okay. Mm-hmm. Okay, so we will see each other tomorrow. If you have more questions, that you can text me on the channel, and I will check it out and explain to you in the Slack channel. Yep. Thank you very much.
So thank you, Dien. Thank you. It was very nice to have an overview about electron scattering on nuclei. It was cool. One message for all the students: we will have this afternoon recap session with Dien and Thomas Britton, the machine learning guy, on Gather, starting at 2:30. So you are free to join us if you want, and to ask more questions to Dien about electron scattering and also their life about research. So feel free to join us if you want. 2:30 on Gather. See you later. Bye bye.